Hello. So in this video, we are going to be talking about vertical asymptotes, and in particular, some techniques that we can use to find vertical asymptotes when it comes to rational functions, with a little bit of an asterisk that the sort of proper analytic way of doing this involves limits, which we're not going to do in this class, so there's a little bit of hand waving that's going to happen, which I'll mention when we get there. So fundamentally, the sort of big tip-off is a function has a vertical asymptote when it's trying to divide a non-zero value by something that we call arbitrarily small, meaning that's something that is very, very close to zero. Okay, so as an example, let's look at a function here, r of x. Now, you might notice, like right away, right, there's some common terms here. Before I do any of that, I'm going to record the domain because, again, to be very clear, domain does not use the simplified version. It uses the sort of original version of the function. But once I have written down the domain, now I can cancel out stuff to get its more simplified version for calculation reasons and various things. So I have a common x plus 1 I can cancel, and I have x plus 3 in the bottom and 2 of them in the top, so I can cancel the one in the bottom and lower the one in the top by 1. Okay, so my simplified form then is that x minus 2 times x plus 3 all over x plus 2. Okay, and it's worth recording here the sort of restrictions on the domain for the simplified version. So here, x can't be negative 2. Now, again, I want to be very clear that the domain is still that x can't be negative 1, negative 2, or negative 3 because that was from the original. This is just a note because this will help me figure out which values are sort of potential vertical asymptotes versus which ones are potential holes, which is something we'll talk about in another video. Okay. Now, because I still have a domain restriction here, I still have a negative 2 as a sort of area where the bottom is 0. That means that that is a potential vertical asymptote. Again, I want to look at areas that are basically non-zero over 0 if I try to plug them in. So I'm going to plug in negative 2 and see what happens. If I plug in negative 2, I get something that equals, and again, this is in quotes because this is not really a valid math expression. What I'm trying to figure out is what would happen if I tried to do this. And the important bit is that I have a non-zero, negative 4, but all I care is that it's not 0, over 0. So trying to plug in negative 2 doesn't work. Not surprising because that's exactly why we chose negative 2. But the important takeaway is that the top is not 0. And this tells me that this thing is going to be a vertical asymptote. So as a shortcut that is incredibly hand-wavy, because again, we need calculus tools to do this sort of correctly, if we try to plug in a restriction like this, right? So we say like, if we try to plug in some value a, where like negative 2 would be the a in this case, and we get something that equals, because again, we can't actually plug it in and say it equals this because it's not a valid expression, but it sort of equals, in heavy quotations, some number k over 0 where k is not 0, i.e. non-zero over 0. And this is sort of the important thing that we're using to do the hand-wavy bit, the top and bottom functions are continuous around those values. So when I look at negative 2, if I looked at just the bottom function, x plus 2, that's a polynomial, continuous everywhere, certainly continuous at negative 2. If I look at the top, right, that's a product of polynomials, so it is also a polynomial. It is also continuous at negative 2. So since the top and bottom are continuous at those values, and trying to plug it in gets me non-zero over 0, that tells me that there's a vertical asymptote at that value, at x equals a. Okay? So again, the sort of idea here is that we would record the domain because we're going to simplify, but we want to know sort of the beginning, the actual domain, which is based on the initial one for reasons of vertical asymptotes and holes. We'll get to holes later. But you also, doing that, right, we have the domain restrictions here, then we can simplify to find sort of what's left as a domain restriction. So negative 2 is still a domain restriction. That's the one we check. If it ends up being non-zero over 0, and both these functions are continuous at that value, continuous at negative 2, that tells me that negative 2, right, that value that we try to plug in, that is a vertical asymptote. That's how we can tell, okay? So vertical asymptote at r of x, that is that x is negative 2, okay? To be clear, we would write x equals negative 2 is the asymptote, because the asymptote's a line, okay? All right, so what do we do? Well, we talked about vertical asymptotes, and in particular, vertical asymptotes are what happens after you simplify everything. You try to plug in a restriction, and you get some sort of non-zero over zero, where, because we don't have calculus yet, we sort of need this stipulation that the top and bottom are continuous around those values. We could do a little bit better once we have calculus, but we don't yet. So that's sort of the definition we're going with at the moment. Okay, so that is that.